Unchecked data growth and data sprawl are having a profound impact on life sciences workflows. As data volumes continue to grow, researchers and IT leaders face increasingly difficult decisions about how to manage this data while keeping the storage budget in check. Stay tuned and learn how these challenges can be overcome through active data management and leveraging cloud technology. In this Infocast, we'll hear one of HGST's subject matter experts discuss real-world data storage challenges in life sciences, the need for rapid access and secured sharing of bioimaging data, and how storage impacts the pace of discovery in genomics. And now, it's our pleasure to introduce David Hyatt, a member of the Health and Life Sciences practice at HGST.
Welcome, everybody. First off, I want to thank San Diego Supercomputing Center here for hosting this event in such a nice facility, and also Advanced HPC for sponsoring. Without them, this wouldn't be possible. So what I'd like to do is talk to you a little bit about, I'm going to set the stage, and then we're going to kind of dive into some of the details of best practices. But starting off, let's take a quick look at some of the life science use cases, the most common ones, and look at the workflow comparison at a very high level, talk about some of the common storage challenges in life sciences that you may be facing, as well as look at the use of next generation storage platforms like Object Store and how that might fit into a workflow, scientific workflow. And then, of course, we'll jump into the best practices. And last, I want to issue a challenge for you guys to think differently about storage. So to start off, the common use cases are obviously sequencing, bioimaging, and also journal archives. When we talk about sequencing, that's typically the key to personalized medicine. The cost of sequencing, we all know, is dropping, and now the real cost is in the analytics. Not only the bioinformatics, but also the systems required to run those analytics. And in bioimaging, it's very similar. We have microscopy, digital pathology, and neuro research. There's an intense focus on curing life-threatening diseases and essentially tracking the mutations of cells over time, capturing those visually so that they can be used for comparison in clinical settings as well. And then, of course, journal archives. I interestingly, last year ran across a gentleman from the National Library of Medicine, and his job is to fly around the world and work with small third world countries and capture and make sure that their medical information and journals are archived for safekeeping because of political instability. So all of those, and when we look at this and consider what this means in terms of storage, it's all about the retention policies. How long does this data live? And generally, it's going from journal archives, which is forever, all the way down to it's dumped in a matter of weeks if it's raw data. But when we look at the workflows, they're similar in many respects, but there's also a lot of differences as well. For example, in sequencing, we have both large files, especially the raw data that's coming off the sequencers, but that's processed over the workflow, and it goes from a very unstructured text format, which is very compressible, down to a more structure as it goes through the workflow and is processed. And of course, the data sizes of BAM and VCF files we know are considerably smaller. In the bioimaging space, though, it's actually a little bit of the opposite, because you start off again with unstructured data, very large. For example, the electron microscopes, the file sizes can be in the terabytes, and if you add time lapse to that, it also increases the size. But those images, as they progress through the workflow, they actually grow, and we're going to talk about why that is in the next slide. But one of the things I wanted to focus on here in terms of the data storage, especially with the life science workflows, is these are traditionally they're file-based storage systems. And given the growth in file sizes, what we're seeing is a lot of growth or interest in object storage. For example, the most common place would be towards the back end here in the data store, where Object Store provides a great platform for data sharing and collaboration. We're also seeing interest in pre-staging. So at the very head end, right off the sequencer, capturing that, depending on the workflows, that data may need to reside off of primary storage for some time. But interestingly, we're starting to see that transition to object storage in the processing space as well. HGST and collaboration with Ghent University in Belgium stood up a big data, a Hadoop cluster, and did some analysis where we replaced the HDFS with an object store and with largely the same performance level. So there is a lot of interest in that area. So when we look at the data challenges, we all know that the growth is a problem, and this kind of illustrates that. The chart on the left-hand side, this, you may have seen this before, but ultimately what it is the global sequencing capacity, and how that's growing. The line on the bottom is Moore's law, so everything above that is really where we are today. The historical line. All I can say is I wish my retirement plan looked like that, but it sure doesn't. It's that the red line is data doubling every 7 months. And in terms of the center line, that's every 12 months, and that's kind of the accepted growth rate. Now, when we look at bioimaging, this is why we have growth throughout the workflow, in the sense that we're starting to add schema and annotating that with metadata in terms of color detail, object level features, topology, information, composition of cell structures. And then certainly there's when we start looking at three-dimensional microscopy images, we have single focal plane, and then we stack those to make that image. And when you go from to a 10 focal plane, it's not just a 10x type of multiplier. It can be 250x. It's very dependent. But the key point here is obviously we have data that's doubling every 7 to 12 months. That is a challenge for researchers. Other challenges that come to mind are rapid access and securely sharing that data. Again, this impacts the pace of discovery through collaborative research. It also, what we're seeing is a lot of growth in shared databases, publicly shared databases and biobanks. There's over 300 biobanks in the world, and that number is growing very rapidly because people are sharing that data and leveraging it for research. It also, more close to home, affects clinical outcomes. And I think my favorite example is the sequencing of a human genome in 26 hours by Rady Institute and Rady Children's Institute and Edico Genome. I think that's absolutely impressive. But more to the point, when I was talking to him yesterday, that wasn't good enough. They're looking to accelerate that even faster, and through not only optimization of the workflow itself, but also in this underlying infrastructure. And so when you think about that, 26 hours for a newborn infant with a 60-day life cycle, let's kind of put this in perspective that you and I could understand. 60-day life cycle, 6-day average turnaround, that's 10% of an infant's life, which would essentially equate to 5 to 7 years to get the results back for you or me. Clearly, in situations like that, time is of an essence, so rapid storage access and securing that information is critical. And so ultimately, we can process data faster by parallelizing it, but ultimately the bottleneck becomes storage. It becomes the storage systems and in terms of scalability.
Thank you for attending our Infocast. From all of us at HGST, have a great day.